All right, good morning. Happy Tuesday. Thank you for coming. I said that already. But anyways, okay, so last week of classes. I can't believe it. I know, it's exciting. Last week of classes, usually it's like a really fun time at school, right? But not this year, probably. So it's just nice to get classes over with, I think. But yeah. Okay, so let's see. I don't think we had anything going on. We're gonna finish trig this week. Hopefully we won't have too much left over for Thursday, because I do want to do a little bit of review for the final exam, of course. Okay, so I'm putting together a practice final, and so I will post a practice final on WebAssign. Today or tomorrow. Kind of depends on how my day goes. It's kind of a busy day today, so I don't want to overcommit, but it'll be there before class on Thursday. How about that? So, okay, so last week we did a tricky section, right? We talked about the other trigonometric functions, right? So for some review, right, we talked about, okay, so we've got our unit circle, right? And then we talked about some key cutoff points. So the halfway mark, the third of the way mark, and 2/3 of the way mark. This was at pi over 6. Oh. This was at pi over 4. And let's see here, this was at pi over 3. Right, so we've got these cutoff points, and maybe I should draw a solid line here, right? And then what we established last day and used was the fact that, okay, well, each of these xy coordinates, right, xy is actually the cosine of, we called it t or theta, right? We said, okay, we've been talking about these distances as if they're distances along the unit circle, and they are, but they are also going to be in terms of angles. So now that we've introduced these angles, I'm going to talk about them as if they're angles, but they are also the distance around the unit circle. And I know that can be confusing, but it's just take it for what it is. So that's the same as cos theta sine theta, right? And so here, right, xy is the cosine of theta, and the sine of theta for all of these, right? And we can keep going around the unit circle, but it stays the same, right? The x coordinate is the cosine of that angle, and the y coordinate is the sine of that angle, right? And so from these two sines and cosines, we can build the other functions, okay? But before we do that, let's just review what each of these points are. These were the ones that you either have to memorize, or you can use the that unit circle that I gave you. It's in the, can't remember what it's called, the trig, yeah, the trigonometry formula sheet. It's at the top of your Moodle page. That's where you'll find this unit circle. And notice we have these points all the way around. And we basically go through these same values of x, just positive or negative, and then the same values of y, just positive or negative. So we can talk about just this quadrant here. And we said, okay, so, and let me just remember how we wrote those. I'll just bring it in. Okay. And maybe I'll just skip that and say that, okay, well here, this tells me that the cosine of pi over 6 is root 3 over 2, and the sine of pi over 6 is 1 over 2, 1/2. Right, that's what those things are telling us. And so we can go all the way around the unit circle and we can pull out these sines and cosines. From sine and cosine, we can build the other trigonometric functions. Okay. So from sine theta and cos theta, we can build the other trigonometric functions. Okay. I'm going to grab that from the handout here. Okay. The other trig functions are these. Now let me see here if I want to, maybe I'll bring in, yeah, I'll bring in this one instead, the fundamental identities. Okay. So, make a little bit of room here so we can write about it. We've got t's in here, right, instead of thetas, but that's okay. You can kind of read them interchangeably. T is used to denote the distance around the circle, but we also know that that is the angle. So, so you can kind of read t or theta, and even when you're doing these problems, you can use t or theta. It doesn't matter to me. So notice that as long as we have sine or cosine or both, then we can rewrite and we can find all these other functions, especially for cotangent. There's actually two ways to get to cotangent, whether you have the tangent of t, which is the sine over cosine, or if you just have cosine and sine, you can construct your cotangent, but then you can also construct your tangent of t, and then you can use that to make your cotangent. So it depends on what information you have. Okay, so what we can do is we can use these identities. So these are our fundamental identities, and what we did last day was we used these fundamental identities in the Pythagorean identities to rewrite some functions in terms of other trigonometric functions, right? And so if you only have cosine, for example, then maybe you want to rewrite tan in terms of cosine, right? And so that's something that we did last day. We unfortunately don't have time to go back and work on that again, but it might be worth reviewing, and it's also in your homework, of course, so you'll have practice there. But we can use the identities to rewrite trig functions in terms of other functions, in terms of other trig functions. Okay. So let's see here. Okay. Okie dokie. We also, right, if we know sine and cosine, right? Then we can use those values to figure out the values of the other trig functions, right? So for example, if I know that the cosine of pi over 6 is root 3 over 2, then I can figure out what the other functions are, right? So the other functions, when I talk about the other trig functions, there are 6 trig functions that we're going to be concerned with. Sine, cosine, tangent, cosecant, secant, and cotangent. Okay, so those are the 6 trig functions. And in fact, we're going to work on those some more right now. So that's why I'm not including it in the review. I'm going to use it fresh. So let's see here. Let's start section 6.2 because I've got a page break there. So I just want to start on a new page here. 6.2 is called the trigonometry of right angles. A right angle is one with a 90-degree angle in it. An angle, or sorry, a triangle with a 90-degree slash pi over 2, right, angle is what we're gonna focus on, right? And so here, what it looks like, how we draw it is if you have something like this, then that little square says that this is a 90-degree angle, 90-degree or pi over 2. We talked about degrees versus radians, and we also established how do we move between the two. I want you to focus your attention on the radians, right? But for this section specifically, we might kind of gravitate towards degrees because it's a little bit easier to think about, right? But we could be in either degrees or radians. Let me just write that down here, right? So here we can be in degrees or we can be in radians. Radians don't really have any units. Sometimes we'll say rad just to emphasize that it is in radians, but if there are no units, then for sure you should be in radians. And so depending on where what angles you're talking about, right? If you have degrees, then your calculator should be in degree mode. And if you don't have any units, or if it even clarifies that you're in radians, then your calculator has to be in radian mode. Okay. So we can talk more about those trig functions. In fact, let's bring it in here, 6.2. Where is it? I made a real mess the other day. I brought all the old things in and it bumped my newer things. Here, I'm gonna jot on this so that it bumps it to the top. Okay, so I'll bring in these trig ratios, and the reason that we want to go kind of in this direction is because we don't always want to be forced to be on the unit circle, right? So we won't always be on the unit circle. So let me bring this in here. We will not always, that doesn't really make sense, but anyways, we will not always be working on the unit circle. So in general, we use these guys. Okay. Some of these might feel familiar, right? Sine is opposite over hypotenuse. That's the so, and then cosine is adjacent over hypotenuse, ka, and then tan is opposite over adjacent, toa, right? So katoa, you might remember SOHCAHTOA. Oops. Which says that sine theta is the opposite over hypotenuse. Cos theta is adjacent over, hypotenuse. And tan theta is opposite over adjacent. We need to clarify, what do we mean by opposite, adjacent, and hypotenuse? Well, you probably remember, but just in case, right? So where adjacent in terms of this angle, right? So there's, in a triangle, there are 3 angles, and we're going to assume that one of them is always 90 degrees, right? So because we're talking about right triangles and right angles. So here, right, that one is cleared up. So we could either be talking about this angle or we could be talking about this angle. But in terms of this angle that we're given here, right, then the side that's opposite the angle is the opposite. The side that's kind of attached to the angle is the adjacent. And then the one that's opposite the right angle is always the hypotenuse. The hypotenuse is always going to be the longest. So where the adjacent is attached to theta, the opposite is opposite theta, and the hypotenuse, hypotenuse is the longest side, and it will be opposite the right angle. Okay. So that's important. So if we know what sine, cosine, and tangent are, right, then we can rewrite them and find that the cosecant is kind of the flip of sine, right? The secant is the flip of cosine, and the cotangent is kind of the flip of the cotangent, right? So if we have the opposite, the hypotenuse, and the adjacent, we can find any of these trigonometric ratios, right? And notice that we're not restricted to being on the unit circle anymore, right? We could have a side that has a length of 14, for example. We can still work with these trig ratios. So, given the lengths of the 3 sides, we can find all 6 trigonometric ratios. So let's do an example here. I want to do one of these. So this question says, find the exact values, so no rounding here, of the 6 trigonometric ratios of the angle theta in the triangle. And let's just have a look here, right? Here we know what the length of all 3 sides are, and the angle that we're interested in here is this one, theta. In 4, we have this angle, and we have all 3 sides, and so we can find all the trig ratios. Notice here for 5, right, I only have the lengths of 2 of these sides, but because it's a right angle, right, I can use the Pythagorean theorem to find the 3rd side, so that'll have to do first, and then I can go ahead and find these trig ratios. And then just because it's easier to see, we're going to do 6 together because the triangle is a little bit larger, so it's easier to see that we're missing the length of one of these sides. So that's what we have to do first, right? So that's the same situation as here. I have to find the length of this hypotenuse, right, before I can construct any trig ratios. But then once I have all 3 sides, then I can put together all these ratios. So we'll do 6 together because it's a nice, easy to look at triangle. So 6. You need to find the length of the hypotenuse. What's nice, hypotenuse. Because it's a right angle triangle, we can use the Pythagorean theorem, right? And so we know that a squared plus b squared equals c squared, where c is always the length of the hypotenuse. Okay. A and b could be either the adjacent and the opposite, or the opposite and the adjacent. It actually doesn't matter. One of those, right? So what we're saying is that 8 squared plus 15 squared, or 15 squared plus 8 squared, notice that they're the same, must be the length of the hypotenuse squared. So that means I have to take the square root to solve for the length of this hypotenuse. So what we have here is that 8 squared plus 15 squared equals c squared. Where's my calculator? Eight squared is 64, and 15 squared is 225 equals c squared. So 225 plus 64 is 289. Solving for that length, right, I have to take the square root of both sides. It is the plus minus, but I need, so technically it is the plus minus when I take the square root. That's always true, but I can't have a negative length, right? And so if you wanted to kind of skip this step, that's totally fine because we do need it to be positive, right? But the length must always be positive. So it's just the square root of 289. So the square root of 289 turns out to be a nice even 17. So what that means is that, okay, let me just copy this here. Copy. Here. So we just found that that length must be 17. Okay. So now what I'm going to do is, because now I have all 3 sides, so now I can start constructing all the trig ratios in terms of theta. So from the perspective of theta here, it doesn't matter what this angle is, we can still find what the ratios are. Okay, so what I'm going to do to save us some writing is I'm going to just copy this here. And here I'm going to clarify that from the perspective of theta, right, then my opposite is 15, my adjacent is 8, and my hypotenuse is 17. So here, my opposite is 15, my adjacent is 8, and the hypotenuse 17. So now, instead of writing all these out, you could say that sine theta is what? It's the opposite over the hypotenuse, so it's 15 over 17. So you don't have to write these out, but I just want to highlight that that's where they're coming from. So if you wanted to write something like, okay, sine theta is 15 over 17, cos theta is adjacent over hypotenuse, so 8 over 17, right? But I'm going to put them in here just so I can see the direct links here. So the opposite is 15 over the hypotenuse, which is 17. Adjacent is 8 over the hypotenuse is 17. Opposite is 15 over adjacent, which is 8. Now, you can see if any of these simplify. I'd probably just leave them with the numbers that we have so it's easier to trace back. But that's up to you. Hypotenuse is 17 and the opposite is 15. Hypotenuse is 17, the adjacent is 8, and the adjacent is 8 over the opposite, which is 15. Okay. Or write it like that. Yeah. So you don't have to write out the opposite over adjacent or the adjacent over hypotenuse part, as long as you're able to map the appropriate side, then you're safe. Okay. So, good. From here, there are some special triangles, but because we've been working with the unit circle, we don't actually need these special triangles as much. They might be useful, but I prefer the unit circle. I'll show you what I mean here. But we don't actually truly need them. Oops, that's not, I'm in section 6.2. Okay, so these angles are in terms of degrees, but if we think about our first quadrant of the unit circle in terms of degrees, right, we've got 90 degrees, and so halfway would be 45 degrees, and then third of the way would be 30 degrees, and then halfway is the 45 degrees, and then 2/3 of the way through we're at 60 degrees. So we can trace those back to radians, or probably rather degrees back to radians. Okay, so we could use these. We could use special triangles, or these special triangles. Use these special triangles, and that's what they're called, special triangles. Special triangles instead of the unit circle, but we only need one method. Right, so this is another method of arriving at those terminal points, but we only need one method of finding terminal points. Okay, so what happens is that note, right, 30 degrees is what in radians? It's pi over 6. 45 degrees is pi over 4. And 60 degrees is pi over 3. Okay. So if we focus on our unit circle, right, then what we could do is we could notice that this, let's focus on this first one first, because it's the nicest one to look at. Notice that it has a length of side 1, and remember the radius of the unit circle is 1. Okay, so this one's probably the easiest to visualize if we're talking about, and you know what, I'm going to grab that unit circle that we just brought in earlier. Copy. And let's see if we can kind of make some sense of this here. But what I'm trying to emphasize is that you really only need one method. And so if you're comfortable arriving at, you know, the cosine of pi over 6 is root 3 over 2, and the sine of pi over 6 is 1/2, and so on and so forth, all around the unit circle, you can tune out for this method. You don't need it. Okay. So what it's saying is that, so what I'm going to do, or try to do rather, is I'm going to trace this guy. Okay. And I'm just going to copy here. See how this goes. Hey, that's like perfectly sized. All right, because remember, this side has a length of 1. Okay. So this has a length of 1 and a length of 1. Okay. And this angle was 45 degrees, which is also pi over 4. Okay. So let's try it again. I know I'm going to have to do a little bit of work on this angle here, but let's see what we can do. So I'm going to copy this again. Copy. And I'll remove this stuff, because now I want to trace this one here. I kind of mucked that up. There. So this is a length of 1, this has a length of root 3, and this has a length of 2. And this is 60 degrees. Okay. Notice that I'm leaving the 30 degrees for a little bit. And I think I'm going to have to stretch this out here just a little bit. Right, I didn't draw very nicely, but I think what you'll see here is that, right, the key part is that this length of 1 has to take up the radius of the unit circle, right? And so, and what we know is that 60 degrees is the same as, right, we just established it, 60 degrees is pi over 3. Okay. Okay, this one's a little bit different, right? Because now I have a length of 1, I have root 3, and I have a length of 2. But from 60 degrees, the cosine of this angle is what, right? The cosine is SOHCAHTOA, adjacent over hypotenuse. What do you know? 1/2, right? So here I'll say, notice that the cosine of 60 degrees is the same as the cosine of pi over 3, which is 1 over 2. And the sine of 60 degrees is the sine of pi over 3, which I'm not going to jot down now, but looking at this, right? Sine is opposite over hypotenuse, root 3 over 2, right? And so root 3 over 2. Okay, so you can either use the special triangles, or like I said, if you're comfortable arriving at, okay, well, the cosine of pi over 3 is 1/2, and the sine of pi over 3 is root 3 over 2, whether you have these points memorized or what have you, it doesn't matter how you get there. As long as you're able to find the sine and the cosine of these angles, I'm happy. Okay, so you can use the special triangles. Same thing here, right? Just coming back to the halfway mark, this length is root 2. So here, right, going back to pi over 4, the cosine of pi over 4 is, adjacent over hypotenuse, 1 over root 2. What I'm gonna scoot this over a little bit. And so notice that the cosine of 45 degrees, is the same as the cosine of pi over 4, which is 1 over root 2. Okay, to make it match this setup here, what they've done is they've rationalized the denominator. And so what you can do is you can multiply by root 2 over 2 to move this square root up to the numerator. And so then what you get is root 2 over 2, which is the same as this guy here. So a little bit of work, but if you wanted to, you could use 1 over root 2 instead of root 2 over 2. They're equivalent, right? Nothing's changed. The value is still the same. Okay, same thing for the sine, right? The sine of pi over 4 is opposite over hypotenuse, 1 over root 2. And so you can use these special triangles if you want to. The one that's a little bit trickier is this angle here, the 30 degrees, or the pi over 6 angle. And I'm going to try to do it here. I'm going to copy, paste, oops, and I wonder if I can just grab this here, because notice that this is at 30 degrees. I wonder if I can just, okay, well, I kind of want it going the other way. I want to flip it. How do I? This is a length of 1, kind of looks weird when it's like that. It's a length of root 3. And this is a length of 2. Okay. So what I'm going to do is I'm just going to flip this, right? Kind of mirror image it, or try to. So this is a length of √3, this is a length of 1, length of 2, and now 30 degrees is down here. So all I've done is I've mapped everything, I've just kind of flipped it on its side, right? Because I don't want to be talking about, you can talk about, right, this guy in terms of the reference angle here, like that, maybe down a little bit, oops. Okay, so we can do that, or what I'm going to do is I'm going to flip it over to the positive side, and let's see if this worked out here. It did not. How about, I'll just draw it on here. Trig, there. How about I do this instead? How did I know where to go to? Well, I know this length has a side of 1, right? So from over here, it's not obvious, but this is a length of 1. So I know I have to go as high as the unit circle, right? And so here, this is a length of, or a height of 1. This is a length of √3, and this is a length of 2, and this is my 30-degree angle. 30 degrees or pi over 6, they're the same. Okay. If we look at the cosine of 30 degrees, right? Cosine of 30 degrees, it's the same as the cosine of pi over 6. Which is, so cosine, adjacent over hypotenuse. Adjacent is √3 over the hypotenuse is 2. What do you know? √3 over 2, right? And the sine of pi over 6 is opposite over adjacent, 1 over 2. What do you know? 1 over 2. Okay. So just to emphasize, they are the same, right? So regardless of how you want to get there, you still need to know these points, these terminal points. But if you prefer to use the triangles instead of the unit circle, that's totally fine. So we see that we can either use the unit circle or special triangles to find cos theta and sine theta of an angle. Okay. Specifically these cutoff points, right? So we don't want to be restricted to these cutoff points, but a lot of things happen at these cutoff points. So usually they're the only ones we end up working with, right? But we can extend this to other angles, right? And so what we can do is before I say what I was about to say here, I'm going to bring in this guy here, copy. It's going to look very familiar because we've already talked about these. Okay, so regardless of if you want to have a unit circle like we did earlier, or if you want to have the special triangles, either way, if your theta is in degrees, then you can convert it to radians. If you're kind of more comfortable working with radians now, that can happen because we've worked so much with radians. And then it lists the sine theta, cos theta, so it lists all the trig functions, all 6 trig functions for each of these angles, right? And so one thing that you can do is just have this table. It doesn't matter if you're using the triangles or the unit circle, have this table ready, and then we can kind of work from there. Okay. So let's see here. Oops, not doing that. I want to do one of these examples. Nothing crazy. So I want to evaluate the expression without using a calculator. So we absolutely can use our calculator for each of these, right? Depending on if you have radians as your angles or degrees as your angles, right? You have to change the mode on your calculator, but you can use your calculator to do all these, but here it says evaluate these without using a calculator. So let's do 29 together. I want to focus on the radian questions because they're typically a little bit harder to wrap your head around, and then you can work on the degree questions. Okay, so let's do 29, which is the sine of pi over 6 plus the cosine of pi over 6. Regardless of how we get there, unit circle or special triangles, the sine of pi over 6 is what? Pi over 6, the sine is 1/2. Okay. Cosine of pi over 6, cosine, root 3 over 2. Okay. So I have 1/2 plus root 3 over 2. I have a common denominator, right? So I have 1 plus root 3 over 2. Good. Let's do 34 together as well. So I have the sine of pi over 3 times the cos of pi over 4 minus the sine of pi over 4 times the cos of pi over 3. And then at the end of the day, it's all squared. Okay. Notice that these aren't the same angle, right? But I've got the sine of pi over 3, and I also need the cosine of pi over 3. I've got the cos of pi over 4, the sine of pi over 4. Some of these, right, from working with the unit circle so much, we just kind of know, right? And so let's see here. Or if you want, there's no harm in using this table. So this is why I give you this table, because regardless of how you get there, we need to know what these values are for these key angles, right? So let's see here. We wanted sine of pi over 3 and the cosine of pi over 4. The sine of pi over 3 is root 3 over 2, and the cosine of pi over 4 is root 2 over 2. So, okay. Let's see here. This is going to equal, I'll put the equal sign down here. Sine of pi over 3, I'm going to put it in brackets here. Sine of pi over 3 we decided was root 3 over 2 times the cosine of pi over 4. Cosine of pi over 4 is root 2 over 2. Root 2 over 2 minus the sine of pi over 4. So just grabbing these from sine of pi over 4 is root 2 over 2. Just grabbing these from the table. times the cosine of pi over 3. The cosine of pi over 3 is 1/2, which I'm just going to grab here before I go up and confirm here. So the cosine of pi over 3 is 1/2. Now that I have these values, you still need to use BEDMAS, right? You need to multiply these guys, then subtract them, making sure you have a common denominator, and then you can square your answer. Okay, so this becomes √3 times √2 over 4 minus √2 times 1, which is just √2 over 4, and then squared. I have a common denominator, so I'm allowed to just go ahead and work some magic here. So I have √3 times √2 minus √2 over 4. And then I need to square that. I'm going to simplify this, right? So I can pull out a common √2, it looks like. So this becomes √2 times √3 minus 1 over 4, and then I need to square that. Oops, my square keeps looking weird. As long as I'm multiplying and dividing in here, right, I can treat the √3 minus 1 as one thing. I can bring the square inside, right? And so this becomes √2 squared times √3 minus 1 squared over 4 squared, putting me at 2 times the √3 minus 1 squared over 16. I think I can keep going a little bit, right? Because, well, I can definitely simplify this, and I'm just going to make sure I'm always hesitant. Yeah, 4 squared is 16. Okay, good. So then I could cancel a common 2 here, right? Because 2 is multiplying all this. But also I can probably expand this a little bit, make it look a little bit nicer. So let's go ahead and do that. The 2 and the 16 can cancel to make 8 in the denominator. And then I've got √3 minus 1 times √3 minus 1. Right? √3 minus 1 squared is √3 minus 1 times √3 minus 1. √3 times √3 makes 3. √3 times -1 makes -√3. -1 times √3 minus √3 plus 1 over 8. Not sure it's simplified so much as I kind of hoped, but 3 plus 1 is 4, and then minus 2 √3. 4 minus 2 √3 over 8. Looks like I can factor out a common 2 here, and then it'll be the end of the road, I think, because then I'll have 2 times 2 minus √3 over 8. I can rewrite as 2 times 4. Right, that's the only way that we could cancel, is if you have common multiples. 2 minus √3, oops, over 4, simplified. There's nothing else I can do here to simplify this, right? So here I'll say simplified. What were we even working on, right? It was a while ago here. Oh yeah, we were finding what this was, right? And so we just kind of worked our way through it and just keep simplifying it. And it might take a while, right? But the first step that you're going to do is just make these substitutions, right? So change the sine and the cosines, exchange them for what their values are, and then you can work with their values instead. So that's going to be the key. Okay, let's see here. I want to give you guys a break because this stuff is really kind of tricky. So how about we take a break until 9:05? Break until 9:05. How about that? Stretch it out. Forget all about it. Oh, that break wasn't nearly long enough. Back to the fun stuff. So let's see here. Ready. Okay. All right. So last thing I wanted to show you in this section is if I ask you to solve a triangle, really what it means is find all the angles and all the sides. Okay. So the last thing that's in here is asking you to solve the right triangle. And so I just want to show you what that means. And then we'll do one together, of course, using radians, and I'll leave those degree ones for you to work on. But I do want to emphasize that what this means, solve a triangle means find all the angles. Oops, I don't know. Means find all the angles and sides of the triangle. Okay. One thing that's important is that, okay, well, the total of these angles, right, has to be 180 degrees. That might sound familiar. Or because one of these is always 90, right, the other two angles have to add to 90 degrees. So in terms of radians, right, the total angles have to add to pi, right, because that's 180 degrees, right? And so, or kind of excluding the right angle, the other two angles have to add to pi over 2, right? 90 degrees. So note, you might recall, because this is kind of, should know this, you might recall the total of all angles in a triangle has to be 180 degrees, which is pi in radians, right? If you think about the half circle, well, that's a distance of pi, right? And in a right triangle, one angle is always 90 degrees or pi over 2, right? So half of that is already kind of eaten up by that right angle. Okay, so this means, wait, what happened there? This means the other two angles must add to 90 degrees or pi over 2 in radians. Okay. That's a step in the right direction, right? If I have an angle in here, which I do in all of these, right? I have the right angle and I have one of these angles, so I can easily find the third angle, right? Making sure that they all add up to pi or 180 degrees. So that's easy enough. And then what I can do is I can use the angles. And just as a note, I would try to use the given angles as much as possible because the other ones you found and they're kind of less reliable, but it doesn't actually matter. But just as a note, try to use the angles that you've been given, right? And then we're given the length of one of the sides. Okay, so then we're hoping to find the lengths of the other two sides as well. Okay, and so what I want to do is I want to work on 42 together, and then I'll leave the other ones for you to do on your own. Remember, you have all these solutions, right? So work through these, and it's kind of low key because you can check against the solutions and you can kind of work backwards. And then you'll be prepared for the assignment. Okay, so what I've been given is that pi over 6 and the adjacent of pi over 6 has a length of 72.3 units. It doesn't matter, right? We're ignoring units right now. So we need to find, first thing we're going to find is, let's find this angle. Okay. And let's call it, what are we going to call this angle? I don't know. Theta, I guess. So solving for theta, I'll do this to show that this is me solving for theta. Okay. So I know that pi over 6 plus whatever this angle is, it has to add up to pi over 2, right? Because overall it has to add up to pi, but this right angle is pi over 2, so that's fine. So I know that pi over 6 plus theta equals pi over 2. So then theta must be pi over 2 minus pi over 6. A lot easier when you're working with degrees, right? 90 degrees minus 74 degrees, easy to find, right? But here we're working with fractions, and so, well, I need to force a common denominator here. I'm going to force it to be 6, right? Because then I can subtract this. So pi over 2 is the same as what? 3 pi over 6, right? 3 pi over 6, okay. So this becomes times 3 over 3. So theta becomes 3 pi minus pi over 6. So theta must be 3 pi minus pi is 2 pi over 6, or pi over 3, right? You can do it this way, right? Or if you remember that pi over 6 is one of those special triangles, right? Pi over 6 is 30 degrees. And then, so here, right? Pi over 6, it's 30 degrees. So then the other angle must be 60 degrees, which is pi over 3, which is what we just found. Right? So it's all here, it's just a matter of putting it all together. Okay, so good. So here theta is pi over 3. Okay. I'll say that theta, therefore theta is pi over 3. Okay. If we let this be A, right? And this be B and this be C, right? The hypotenuse is usually denoted by a C. So then we know that, okay, if I let A be 72.3, B is some length, and let's pick a different color here, I guess maybe light blue. C is the hypotenuse. Okay. So what we can do is we can say, okay, well, right, and I'm just naming these so that I can refer to the specific sides. Instead of calling this the opposite of pi over 6, I can just call it B, right? And so B is the opposite of pi over 6, and the adjacent of pi over 6 is 72.3. Okay. So to solve for B, I know that the B is the opposite of pi over 6. I also, and we're given the adjacent of pi over 6 is 72.3. Okay. So, okay, so if I have the opposite and the adjacent, can't I use the tangent, right? Opposite over adjacent. There are lots of different options that you could use, but you want to make sure that you incorporate as much given information as you can, right? So pi over 6, and I know the adjacent, and let's try to find the opposite. You could try to find the hypotenuse if you wanted to, that doesn't matter. But then you would have to have, okay, then the hypotenuse and the adjacent, which is the cosine, right? So it depends on where you want to start. So what we have is that we know that the tan of pi over 6 is the opposite over adjacent. But we also know that the tangent of pi over 6 is, well, we could take it from the sine over the cosine, or I can just grab it from that table that I gave you, right? So the tan of pi over 6 from this table, I'm at pi over 6, right? The tan of pi over 6 is root 3 over 3. Okay? So I can replace that tan of pi over 6 with root 3 over 3 and see if I get anywhere with that. Scroll back down here. Right, this I can replace with root 3 over 3. And the opposite is the B that I'm trying to solve for, and the adjacent is 72.3. Okay. So then I have root 3 over 3 is B, which I'm trying to solve for, over 72.3. To solve for B, all I need to do is multiply this 72.3 over, and so then I find that B is 72.3 times the root of 3 over 3. I'm pretty sure that doesn't simplify nicely. 72.3 divided by 3. It doesn't really. It's 24.1 times the root of 3. I'm just going to leave it like this. Or maybe I'll say, or 24.1 root 3. Either way, it's not very nice, but it is a number, right? But if I approximate that, 24.1 times the square root of 3 is roughly, so B is roughly, and I think it asked for the exact values. I can't remember. It didn't. So maybe we can use approximate values. In WebAssign, it'll clarify if it wants the exact values or the approximate values. because 72.3 is a decimal, that's why I feel comfortable going for B as a decimal as well, okay? But just as a note, right, this is your, these are, or rather, this is the exact answer. And maybe what I'll do is I'll just, let's do the approximate answer. 72.3 times the root of 3. I'm just going to grab it again, divided by 3. 41.7424446. And of course, it keeps going. So this is the approximate answer. Depends on what it asks for, right? But just in general, because 72.3 is a decimal, we are probably going to be able to use B as a decimal as well. So here, I'm going to say B is roughly 41.74, right? At least 2 decimal places, as many as you can kind of muster, but let's use it to 2 decimal places. Okay, good. There's only one thing left to solve for, right? And that's C. So we have B, it's 41.74, right? I know theta is pi over 3, and I know C, there are lots of different ways that I could find C. I am going to use the Pythagorean Theorem, right? 72.3 squared plus 41.74 squared must be C squared, right? So there are lots of ways that we could solve for C, but I am opting for the Pythagorean Theorem. Okay. There are many ways to solve for C, right? You can play around with it, but I will use the Pythagorean Theorem. Which is a squared plus b squared equals c squared. We said 72.3 squared plus 41.74 squared equals c squared. Right? So solving for C here, knowing that this is going to be an approximate answer because I've already rounded B, right? So it is a little bit off, but maybe it's close enough, right? Let's see here. So C squared is going to be 72.3 squared, which is 5227.29, plus 41.74 squared, 1742.2276 is C squared. Adding those two up, C is the square root. And again, at this point, I'm just ignoring the negative version because I know it has to be positive, right? It has to be some length. So I know it's going to be positive. So I'm just ignoring the negative option of the square root. And I'm taking the square root of 6969.5176. And once I take the square root of that, C is roughly 83.48363672. Or I'll round to 2 decimal places again, just because it looks like a nice cutoff, right? It captures a lot of activity. I don't want you to round too quickly because you want to capture some activity here. So 2 decimal places is kind of the minimum. 83.48. Okay, So now we have solved this triangle. Copy. So we have now found the lengths of all sides and all missing angles. So we have solved the triangle. We have solved the triangle. Which, if we kind of jot this down here, this angle was pi over 3. This length was 41.74 roughly. Oh, I used the wrong color here. Not that it really matters, but could get confusing. There. And a length of 83, oops, 0.48. Right. We have all three sides, we have all angles, we solved it, right? So you can work through some of those sometimes, right? As long as you have 2 out of the 6 as well, and I'm not including the right angle, it has to be a right triangle for this to work, right? But as long as you have information for 2 things, those 2 things could be just the sides, right? Using the sides, you could find the angle, right? If you have this side and this side, you could find the opposite over adjacent, right? And then you can find the angle from there. And then if you have that missing angle, you can find this angle, and so on and so forth, right? So you can kind of pick apart everything that's going on here. Okay. Just briefly, I want to talk about the graphs of trig functions. We're not going to go too deep into it, but I just want to talk about some key features of trigonometric graphs. And so section 5.3 is on trigonometric graphs. Okay. If I had to graph the cosine function, the cosine of theta, well, I have these, if I move around the unit circle, right, I have these x coordinates as I move around, right? But we notice that it becomes cyclical, right? And so every distance of 2 pi, I start over, right? The cosine becomes the same x value that we started with on the first lap around, right? So sine and cosine are what we call cyclical functions. Sine and cosine are cyclical. How do I spell cyclical? I don't know if I even have it on here. No. Cyclical. Cyclical. Anyways, they are. No, I cannot. This one I wish it had spell check, so it could have like a little red line under here and tell me you spelled that wrong. It's bad. So cyclical functions, all that really means is that they're going to repeat themselves, right? Which means before I post the notes, I'm going to go back and change this so I spell it properly. In fact, how about I look it up right now? Cyclical. Haha. Cyclical. Looks better. Thank you. Thank you. Okay, you got it. Phew. I know, it looks like even spell check made it wrong in the chat here. Thank you, Karen Freed. All right. So sine and cosine are cyclical, which means that they repeat over some period, which means their values repeat over some period, right? So in the case of the unit circle, right, they repeat themselves every distance of 2 pi, right? So in the case of the unit circle, the period is 2 pi, right? You have to go the distance of, so the x and the y values keep changing until you're back at the standard position, which is on the positive x-axis. Then you start all over again, right? So in the case of the unit circle, the period is 2 pi, right? Since it takes a distance of 2 pi to start over again. Since the length of one rotation around the circle is 2 pi. Okay. So what happens is that we can kind of flatten this out, and this is hard to visualize, but you can kind of flatten out these trips around the unit circle, and we can map out the sine and the cosine functions. So the cosine of theta is, now let me see here. Where are these notes? 5.3. Oh, again, they're way down here. Bump it to the top. Okay. So what we have is that we can use the, oops, the graphs. I'm going to work backwards a little bit here. What you can do is remember the cosine of theta is the x value, right? So we start at an x of 1, right? And then our next x value is at pi over 6 is a little bit less than 1, right? And then pi over 3, pi over 2, and then what happens is after pi over 2, our x's become negative, right? And they're decreasing to -1, right, as we go to a distance of pi, right? So you can kind of coordinate this, you can think of this graph as kind of a smooshed out version of the x values on the unit circle, right? Then what happens is if you map this out, right, cosine starts at 1 because we start in standard position on the positive x-axis. So cosine starts up here at 1, and then it's got this kind of wavy function, and these waves keep going forever and ever and ever. You can move in the negative direction, right? That's just saying, okay, now move clockwise around the circle, right? And so what happens is once you've gone a distance of 2 pi, so the full unit circle, then you start over again, right? And then you go around the circle again, and then you can go another distance of 2 pi, and it just repeats itself over 2 pi, right? Same thing with sine. If we grab the sine graph, the sine is the y value on the unit circle, right? And so the y value at the standard position is 0, right? And then again, we move around the unit circle and it just kind of fluctuates, right? So our y values are positive, 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 positive. Then after pi, we move into the negative y values all the way to 2 pi. And then we repeat itself, or it repeats itself. So we also have a distance or a period of 2 pi. So both of them have the same period because they repeat themselves over the distance of 2 pi, but sine starts at 0, 0, whereas cosine starts at 1, right? So from the unit circle, we know that if we have something like this, that here, if we start here, this is at 1, 0, which means the cosine of t is 1 and the sine of t is 0, right? And these are the starting positions for the graphs. These are the starting positions for the graphs. Okay. Good. I also sometimes, to remember which graph starts where, because it's going to matter if you start at 1 or if you start at 0, right? Because if you start at 1, like cosine, then after 2 pi, you have to end at 1, right? Whereas if you start at 0 and then you go a distance of 2 pi, you have to end at 0, right? And so depending on which function we're talking about, that's going to matter. I sometimes will remember this as if I have the sine and cosine graphs on the same graph, they come in alphabetical order, right? Cosine would come before sine, so cosine is above sine. That's just how I remember it, but however you want to remember which one starts where is fine by me. So I just want to talk about some of the terminology around graphs, and then we'll do more examples next day, but I just want to introduce them because you will have to do this on the final exam where you have to find the period, the amplitude, and the horizontal shift. Okay. So if you have a sine or a cosine curve, you're not going to have both. It's just going to be one, okay? Then we're going to be able to talk about the amplitude, okay? The amplitude is the distance between the x-axis and the highest point of the curve, or the absolute value, which would take the lowest point of the curve. But usually I just think about the distance from the x-axis to the highest point, which on the unit circle, right, is going to be the 1. That's the highest point. But that can change, right? We can have kind of more stretched out sine curves or more smooshed cosine curves. And how that's going to be affected is by this multiplier outside. Okay? If you have some constant k has to be greater than 0, multiplying x minus b, that k is contributing towards the period, right? So if you have a k that is 3, now your period is 2 pi over 3, so it's quite a bit shorter, right? And then the horizontal shift is how much did this graph shift. So I want to bring in, because I'm pretty sure, oh yeah, here, this one. So here's an example, right? The amplitude is going to be the distance from the x-axis up to the highest point. It looks like 3 in this case, or the lowest point, but the absolute value. So that distance is 3. Here, notice that we've gone a full cycle. So we've gone from y equals 0 back to y equals 0. Notice that this is a halfway point, right? We still have to go through the negative versions as well, but now I've covered all that, all the possible y values. Okay, so the period here is pi. So how is that reflected? Well, it means that we have a multiplier of 2 outside here. Okay. The horizontal shift, or sometimes it's called the phase shift, is that b. Now that b, you're going to pull from here. Okay, so, and remember, it's x minus b. Like I said, we're going to do an example, but let's do, so for today, let's actually just go through and do this guy here. And then next day, I want to definitely focus on 40 for sure next day. Okay. So let's do this one now. And then something like 40, or the one we're just about to do, that's what you have to do on the final exam. So that's why I'm kind of forcing us to look at these, ignoring some of those other questions because they're just building up to what we're about to do. So here, I'll put these in order because this graph is actually having to do with this question. Okay. You will have to find the amplitude, the period, and the horizontal shift if I give you some equation. Okay. So on the final, you will be given an equation and asked to find the amplitude, the period, and horizontal shift. Okay, of either a sine or a cosine function. Of either a sine or cosine function. But they behave the same way, right? So in this case, I have a sine function, right? So what I'm going to do is I'm going to rearrange this thing until it looks like this, right? So for this example, I have this. So for this example, cut out that little blip. We're given this, and what we have to do is we have to work this, rearrange this, rearrange this to match either this one or this one, depending on if you have a sine or a cosine. In this case, we have a sine, so then we want to rewrite it to match the sine version. Okay. the key is that the x has to be on its own, right? And then if I'm adding or subtracting a b, well, if I'm adding some constant to x, then my b has to be negative, right? We've seen that before. But the key is here, notice x must be on its own. Okay, so if it's not, and that's what's going to happen in example 40, where we're going to start next day for review, we have to factor out that multiple that's in front of x and make that our k. But in this case, right, I've got, okay, I can rewrite this. So I've got y equals 3 sine times 2 of x minus pi over 4. So if I have to match these things, right, I see that a equals 3, k equals 2, and it looks like b, I can just write b as pi over 4. Oops. Okay. So now I can take this a, k, and b, and I can construct my amplitude, my period, and my phase shift. Okay, so here, it's important that you don't just use those values straight up. You have to say, okay, well then my amplitude is the absolute value of a, which is the absolute value of 3, which is 3. So that's how you're going to get to the amplitude. The period is 2 pi over k. Okay, so that's important. That's probably the thing that people miss the most, is that it has to be 2 pi over k, and k in our case is 2. So 2 pi over 2 means we have a period of pi, meaning it repeats itself in a shorter distance, which means it's kind of happening faster than our usual unit circle. So it's all relative to how we behave around the unit circle. And maybe what I'll do is I'll try to put these side by side so that you can kind of look at them side by side here. And then the horizontal shift is b, which in our case, so here it is just what b is. So now we're kind of back to easy street here. So the horizontal shift is pi over 4, meaning we move it to we shift it in the positive direction, pi over 4. Positive is a shift to the right. Okay. So that's how we were able to make this sketch, or we didn't, but they did, right? So we have this horizontal shift. So instead of starting, we've got sine, which typically starts at 0, right? But now we've shifted it over by pi over 4. So now we start at pi over 4, and then we go up as high as 3 because that's the amplitude. And then a full cycle is going to take a distance of just pi instead of 2 pi. So try number 40. So from here, try 40 on your own. We will do it as review we will do it as review on Thursday. Done. If you have any questions, let me know. Otherwise, I'll see you for our last class on Thursday.